Welcome to this explainer. Today, we're diving into something absolutely fundamental. We're breaking down the basic building blocks of computer science. We're going to see how code, at its very core, is really just a beautifully structured way of organizing information and doing some pretty basic math. If you've ever wondered how the software you use every single day manages the massive amounts of data it handles, well, you're in exactly the right place. Okay, so let's think about a giant digital filing cabinet for a second. How exactly does your computer actually remember the data you feed it? I mean, whether it's tracking a high score in your favorite video game or just saving a text input like a player's name, your computer absolutely needs a systematic way to store, locate, and update that information on the fly. So, here's our quick roadmap for today. First, storing digital data. Second, choosing data types. Third, the math engine. Fourth, visualizing the code. And finally, number 5, real-world applications. All right, let's jump straight into Section 1, storing digital data. We've got to start with where this data actually lives. So, the main thing to grasp here is that a variable is really just a named folder, an identifier basically, sitting inside your computer's memory. Think of it like a tiny reserved VIP area set up by the computer just for your data. And the real beauty of a variable is literally right there in the name. It varies. The information held inside this folder can update and change the whole time a program is running, just like how a player's score keeps ticking up as they collect points in a game. But, not all data should change. While variables are designed to be swapped around, constants act way more like a locked vault. They are named memory locations, sure, but for data that remains completely fixed while the program runs. Think about something like the mathematical value of pi, or maybe a set currency conversion rate. By setting this up as a constant, you're basically putting a lock on it, protecting that value from being accidentally messed up by other parts of your code. Moving on to Section 2, choosing data types. This is all about reserving the exact right amount of memory for our data. Now, to reserve that perfect amount of memory, we have to tell the computer exactly what shape of data is going into those folders. You've got integers, which are your whole numbers, real or decimal types for fractional values like currency, char or character for a single symbol, strings for full textual data like words or sentences, and booleans, which just handle a simple true or false condition. Declaring these up front is called strong typing. It's absolutely crucial because it lets the compiler check for mismatches and makes your code run much, much faster. Now, here is a super common and honestly sometimes catastrophic beginner mistake. Things like phone numbers or ISBN barcodes on books are what we call pseudo numbers. Even though they look like numbers and are made of digits, they aren't actually meant for math. So they must be stored as strings. If you try to store a phone number as an integer, the computer's going to do what it does best. It'll treat it like a math problem, delete any leading zeros, and just totally ruin your data. No way around it. Okay, Section 3, the math engine. Let's look at how we actually manipulate all this data. We're all pretty familiar with standard addition, subtraction, and multiplication, right? But division gets kind of interesting in coding. Standard division can give you fractional decimal values. But integer division is incredibly useful when we strictly need whole numbers and a remainder. Think about it. If you're organizing a school trip for 230 students and a large bus holds 52 students, standard division gives you 4.4 buses. That doesn't help anyone. You can't exactly hire 0.4 of a bus. You need integer division to tell you exactly how many full buses you need and how many kids are left over. So to do this properly, we use very specific operators. When we're writing pseudocode, we use the term div to represent the quotient. Basically, this just tells us how many times a number fits perfectly and fully into another. Back to our bus example, 230 div 52 gives us exactly 4 full buses, nice and clean. And then, to handle the leftovers, we use mod for the modulus. This operator captures the exact remainder that didn't fit into that whole divide. So for those buses, 230 mod 52 leaves us with a remainder of 22 students, who are definitely going to need a smaller bus. Let's look at how this builds with another practical example. Say you need to convert 500 minutes into hours and minutes. 500 div 60 gives us exactly 8 whole hours, and 500 mod 60 leaves us with the remaining 20 minutes. See, it's just a clean, perfectly logical way to manipulate numeric data without dealing with messy decimals. Up next, Section 4, visualizing the code. Let's map out how all this flows together. To really grasp how this all comes together, we can visualize the hidden processes of code using a flowchart. Take a look at this one for a simple multiply machine. We start right at the top, declaring and initializing our variables to set up those digital folders we talked about. Then we take in our user inputs. Next up, the processing happens. That's where the math is actually calculated behind the scenes. And finally, we output the result for the user to see. Notice how this algorithm perfectly follows a highly logical sequence. Declare, input, process, output. This is basically your golden blueprint. You're going to use this exact four-step sequence to complete almost any fundamental programming task out there. And finally, Section 5, Real-World Applications. Time to solve some actual problems. But actually, right before we build our real-world system, we really need to talk about documentation. In code, we use comments, which are usually denoted by double slashes or an apostrophe. The cool thing is, the computer completely ignores these comments when it's executing the code. This makes them the ultimate tool for explaining your logic, leaving little reminder notes for your future self, or even commenting out lines of code to safely test out new solutions without totally deleting your previous work. All right, let's put our four-step blueprint into action to find the volume of an aquarium. Step 1, we declare our variables for height, width, and depth. We set these as real numbers, since measurements usually have decimals. Step 2, we input those numbers. Step 3, we process. We multiply the inputs together to find the total cubic volume, and then divide by a declared constant of 1,000 to convert that into liters. And step 4, we output that final number. It's just perfectly logical. And the exact same logic applies to something like a cinema ticketing system. First, we declare integer data types for the number of attendees, because, well, you can't exactly have half a person show up to a movie. We take those inputs, apply a standard admission constant, and then use our arithmetic operators to calculate the varied decimal discounts for kids and seniors. Add it all up and output the total income. Simple, right? Ultimately, programming at this level isn't some sort of dark magic. It's really just a digital mirror of how human beings logically solve problems every single day. You identify the data you need, you store it safely, you process it, and you deliver an answer. Every massive app or complex piece of software you use is built on top of these exact same foundational folders and basic math operators. So knowing how simple the building blocks truly are, what problem in your world is just waiting to be automated next?